All right. Most people have checked in, so I'm going to go ahead and get started. Um, a note on the homework, which is like the only question that people have been asking. Where do I turn it in? I just changed the number of downloads you can have or uploads you can have, and I also changed it to you can submit um, up until like 11:59 tonight. Okay, so if you need to go and do that real quick, just submit it. So it's all in the same place. Um, that's yeah. So you're gonna submit it still to on campus. I changed the number of uploads you have, and you should be able to resubmit it. So if you haven't done that, please do that. Otherwise, today we're gonna get into some newer stuff, which is a little bit more like visible to you. Okay, sequences and series is really just kind of playing with numbers. These counting principles actually has to do with real life stuff. Not that sequences and series don't, but it's these counting principles are very tangible in a lot of different ways. Okay. Um, and quickly, I guess before we do that, really quickly, what we did last week, our last class, um, we reviewed this stuff. This should be down pretty easily, but then we get into binomial coefficients. Okay, so expansions of binomials, right? They happen in a pattern, and we need to know that pattern. Okay, exponents of x will decrease as you go right. Exponents of y will increase. Um, each of these blue terms is some combination of numbers, right? So NCR is always going to be that um, coefficient, but you can also kind of use Pascal's triangle. And I think it was Hudson who asked, how do you get each of these numbers, like in later terms? Each number is the sum of the two numbers above it. With ones on the outside. Okay, so if you like really want to do this, you can, but overall we do need to know how to find it. Because if I said like find the 15th term of like the 20th expansion, doing that Pascal's triangle is going to be a pain. How do we submit the homework? Again, to on campus, you go to the assignment and there should be a place to submit it. So that's what we did last week, and it doesn't seem like there's any questions on it. If there are, we can go back and do it later. Again, I'll be available on Teams after this, so that'd be a great time to ask. Um, and I think the most important thing that we can get out of this though is the combination stuff, which we're actually going to get into a little bit today again, just in a different way. Okay, so if you can just remember this equation, maybe have it in front of you, like if you're starting to take notes, have that equation out in front of you, and it'll be pretty helpful. Okay, so today we're going to go over counting principles, and again, this is one of the more tangible things uh, in this chapter, and it's getting to probability. All right, so counting principles, and in order to introduce this, I've got this scenario, and we're going to count the number of different ways something can happen. Okay, so in this example, 8 pieces of paper are numbered 1 to 8 and put in a box. One piece is drawn from the box, the number is written down, and then the paper is put back. Then another piece of paper is taken from the box, the number is written down, and the piece of paper is put back. Okay, and I want to know how many different ways can you get a sum of 12. And then in a little bit, we'll go over that second question. What if two numbers are drawn at the same time? Okay. So how many different ways can you get a sum of 12? Well, the easiest way to do that is to just list the number of ways. Okay. So if we do that, well, we need numbers that add up to 12 from 1 to 8. Okay. So the first number that comes to mind for me is 4 and 8. Right, so if we get 4 on the first paper and 8 on the second, those two numbers add up to 8, or to 12. Okay, the next is 5 and 7. So 5 on the first paper, 7 on the second. Then we can get 6 and 6. We can also get 7 and 5. And we can also get 8 and 4. So in those orders, we can get sums to 12, right? So again, that first column, these are the first pieces of paper in blue and the second pieces of paper in red, right? So I know this seems kind of simple at first, but does everyone understand what I just did? So overall, there are 5 ways to get the sum of 12 given the scenario, right? And in the second example, I ask, what if the two numbers are drawn at the same time? So there's no replacement. Do you have to write down 6 and 6 again? We don't have to write down 6 and 6 again because there's only really one way to get it, and that's if we draw 6, put it back in, and then immediately draw it again. That's kind of the same. That's the same role, if you want to call it that. Okay, that's a good question. Stuff like that can get a little bit confusing later on, but as long as you stay organized and kind of just know that anything that looks like this, they really can't flip-flop. Like they can, but it's the same thing. All right, and we'll kind of see that here in a little bit. All right, so what if these two numbers are drawn at the same time? How many different ways can we get a sum of 12? Well, it's almost the same thing, right? So we can get 4 and 8. We can get 5 and 7. But in this case, we can't get 6 and 6 because there is no replacement, right? We take one number out and we never put it back in. So in this first case, we draw a 4 and just leave it outside the box. And then we pull another number and we get 8. Okay. In this second case, we pull a 5 from the box. We don't put it back in. Then we pull another number and we get 7. We can't get 6, keep it out of the box, and then pull another 6 because that another 6 doesn't exist. Okay, and then the other two ways are again 7 and 5 and 8 and 4. So there are only 4 different ways. And this, again, this seems kind of simple. It doesn't seem like there's really any math to it. It just seems like logical. But this is what probability really boils down to. It's getting the number of different ways something can happen and then taking that as your denominator with a kind of a wanted outcome in your numerator. So that's kind of where we're headed. All right. And again, this can be confusing. So please ask questions. I'm okay with that. I'm going to try and move a little bit slower. And I'm going to urge you guys to get on Teams and ask questions later. But this is what we're going to be doing. Okay. And I have a couple of different examples and we'll move through some definitions as we go. All right. And the first one is this fundamental counting principle. Okay. So this applies to everything. And what this says is that if we have two events, E1 and E2, where the first event can happen in M1 different ways, and the second event can happen in M2 different ways, the number of ways that those two events can happen is M1 times M2. All right, so I'll give people kind of a second to write that down because that is super important, and it can be used in a lot of different ways. So again, let E1 and E2 be two events. the first event E1 can occur M1 different ways. After the first event happens, the second event can occur M2 different ways, and the total number of ways that the two events can happen is M1 times M2. So you're just multiplying the number of different ways that those two events can happen together. Okay, so my example that I have on here is how many different pairs of letters can happen in the English alphabet. Okay, so there are 26 different letters in the English alphabet, and I like to draw this stuff out. I don't like list all the different pairs of letters, but I do like to draw the different events. Okay, so these two boxes represent E1 and E2. So if we're just getting pairs of letters, we need to figure out how many different letters can happen in the first position. Okay, and the first position letter can happen 26 different times because there are 26 different letters in the alphabet. The second event, or the second position letter, can also happen in 26 different ways. So the total number of pairs are these two things multiplied together, which if you do that, you get 676 different pairs of letters in the English alphabet. Okay, so questions about that, because this is super important, and just getting this basic understanding of this example is crucial. And this type of problem shows up a lot on the ACT, and normally it shows up in the way, or in the form like you have 3 different shirts, 4 different pairs of shorts, and then like 2 different pairs of shoes. And how many different ways are there to dress? Okay, and all you do is multiply those 3 things together, and you get an answer, right? And that's because in that case there are 3 different events. But we will kind of move on from that into a little bit harder of an example, and that's telephone numbers. All right, so I want to see how many possible telephone numbers are there in a single area code. All right, and there are rules for telephone numbers. All right, so right now we're not worried about the area code. We're in one single area code. And the rules for all these numbers is that our first digit cannot be 0 or 1, and it obviously has to be like a single number. So not like 10, 11, 12, or 100 or whatever. It has to be a digit. But that digit cannot be 0 or 1. And then the next 6 numbers are anything from 0 to 9. And we want to find out how many different possible numbers there are within this area code. Okay, so each of these boxes is its own event, right? So this first box has 10 possible outcomes, but we're going to delete 0 and 1. So there's really 8 possible different outcomes. Right, so digits from 0 to 9, that's 10. So 0, 1, 2, 3, all the way up to 9. There's 10 digits. And we're taking away 2 of those. And then every other digit can be any digit from 0 to 9. Right? So there are 10 possibilities for the second, 10 possibilities for the third, 10 possibilities for the fourth, fifth, sixth, and seventh. So the total number of different telephone numbers within an area code is all of these numbers multiplied together. So 8 times 10 times 10 times 10 times 10 times 10 times 10. Okay, so if we do that, we have 8 and then times 10 to the 6th. Which means there are 8 million different possible telephone numbers within a single area code. All right, so in St. Louis, there's several different area codes. 314 and 636 are like the most common, I think. And there aren't anywhere near 16 million people within St. Louis. Okay, so that covers like pretty much any situation possible, right? But I'll pause there for a second. Does that example make sense? Where we have different events and we are multiplying the number of different ways each event can happen together. All right, another counting principle that we need to know is what a permutation actually is, right? So a permutation of some number of elements is an ordering of those elements such that there are first, second, third, and so on positions. All right, so if we have A, B, C, D, E, and F, and we want to see how many different orders there are for that, we could write down all the different orders. All right, so we would A, B, C, D, and E, and F. The next order might be B, C, D, E, F, A. The third would be C, D, E, F, A, B. But then you get stuff like F, D, C, B, A, E, right? There are all these different orders, and you can do that systematically, but it's going to take a really long time. So instead of doing that, what we can do is we can split each of these positions into different events. Okay, so there are 6 different positions in A through F. And we want to see how many different orders there are. So again, we use that fundamental counting principle to do this. Okay, so in the first position, we can have any number, or we can have any of these 6 letters. Okay, so there are 6 possible letters that can go in that first position. After we use that first letter, well, then there are only 5 left. So in the second position, there are only 5 different letters left for that second position. And then once we take away 2 of those letters, there are 4 left. Once we take 3 away, there are 3 left. And then 2, and then there's only 1 left. So if we multiply all those together, this looks a whole lot like 6 factorial. Which, if we do that math, we get 720 different orders. Okay, so I want to pause there real quick. Does that make sense? All right, so a shortcut of this, if we're asked how many different orders of n things there are, so the number of different permutations of n elements, all we really have to do is take the number of elements and take the factorial of that. Okay, if there are no questions, I want to move on just a little bit to something like kind of just a step up from this, right? And that is using these counting principles and these permutations in order to find out the number of different orders there can be with a larger number of elements. Okay, so for example, and what I mean by this, say there are 16 people who race at the 1600 in the 1600 meter at state. Okay, so 16 total people. And how many different ways can those 16 people come in first, second, and third? So if you just think about this for a second, we have 3 different events. We have first place, we have second place, and we have third place. If we follow that same kind of procedure that we just did above, there are 16 possible people for that first place position. Right? So this first event can happen in 16 different ways. The second event, because we already used one of those people, can only happen in 15 different ways. And then the third event, because we've already used 2 of those people, can only happen in 14 different ways. So again, if we multiply those together, we get 16 times 15 times 14. There are 3,360 different ways that 16 people can come in first, second, and third. Questions about that? All right, so this is kind of a subset of permutations. And what it boils down to is this equation. And kind of like combinations, it's very, very similar. All right, so permutations of n elements taken r at a time. It's said to be NPR, n permutation r. And it ends up being this equation. So from above, we had a total of 16 people, and we wanted to see how many different orders there are if we take 3 of them. So we would plug it into this equation. So we have 16 factorial over 16 minus 3 factorial. And if we do that math, it ends up being 16 factorial over 13 factorial, which simplifies to 16 times 15 times 14, which is exactly what we got up above. Questions about that formula? Okay. And there is an equation for distinguishable permutations. We're going to save that for now and move on just a little bit back to combinations. Okay, so we did combinations in reference to the binomial theorem, right? In order to find a binomial coefficient, you use this formula. So from the nth expansion, we're trying to find the rth coefficient. We can do it that way. But there is also another meaning for combinations, which I forgot to erase all this. Okay, so combinations of n elements taken r at a time, which means that we have n elements and we're choosing r of them. Okay, so what I like to think about is let's say cards in a deck. Right, there are 52 cards in a deck and we're choosing 5 of them, which we'll get to that example here in a second. But we want to find out how many different combinations of 5 cards are there within a 52 card deck. So if we randomly shuffled them, how many individual combinations would we get without order mattering? All right. So for example, in how many different ways can 3 letters be chosen from the letters given right here? Again, just like in permutations, we could actually list those combinations. Okay, so we could write them down as kind of in a systematic fashion. So if we keep A first, our first one would be ABC. Then we could have ABD. Then we can have ABE. Then we could have ACD. Then we could have ADE. Then we can have B be the first. So BCD, BDE. Actually, I'm going to do BCE first. Then BDE. And then we have C, D, E. Okay, so writing all these out is kind of tedious, and it's a little bit hard if you don't know kind of the system to do it. But we could count all of these. And I missed one. Ah, yeah, there should be an ACE here. Okay, so we could list them and count them, and we would get 10 different combinations of 3 letters given those 5 letters. Okay, now notice that order really doesn't matter here. A, B, C, as far as combinations are concerned, is the same thing as CAB, which is the same thing as CBA, right? Those are not distinguishable, or those are distinguishable. Like they're not, they're the same thing as ABC. Okay, so we don't need orders. We're not worried about orders here. We're just worried about the three things that we choose from 5. Okay, so there are 10 there. Another way to do this, though, is to use that binomial coefficient equation. Okay, so given n elements, where we want to choose 3 of them, we can plug it into our formula for n choose r. Which, if we do that, well, first, I guess recall, this is n factorial over n minus r factorial times r factorial. So if we plug that in, we would have 5 choose 3. Which will be equal to 5 factorial divided by 5 minus 3 factorial times 3 factorial. And when we do that, and we expand a little bit, yeah, 1 times 2 all the way up to 5. 5 minus 3 factorial is really 2 factorial. And then 3 factorial is 1 times 2 times 3. So then we can cancel out some common terms. 1 through 3 cancel with this 1 through 3. And then we have 4 times 5, which is 20, over 2, which is equal to 10. Which is the same number that we got just from listing them. But this is just a little bit easier, right? It's a little bit more straightforward, and you don't have to like systematically do anything. It's just taking numbers and choosing other numbers. So while that example isn't necessarily interesting, I do have another one that might be a little bit more. All right. So I don't know how many people played poker. I know a couple of guys that were on Kairos with me played cards. We never actually played poker. But for those who haven't, you should know that gambling is really only gambling if you don't know the outcome or don't know the possible outcomes. Okay. And one way to do that is called counting cards. And this isn't counting cards by any means, at any stretch of the imagination, but it's kind of the foundation of it, which is really just probability. Okay, so in poker, you have a 52 card deck. And you are given 5 cards. All right. And if you shuffle the deck a bunch of times and hand out 5 cards, I want to see how many different combinations of 5 cards there actually are. So if we do that, we would have 52, and we would want to choose 5 cards. So if we write that out, if you expand that a little bit, it would be 52 factorial over 52 minus 5 factorial times 5 factorial. And if we expand that just a little bit, we would get 1 times 2 times 3 all the way up to 52. Over 52 minus 5 factorial is really 47 factorial, which is 1 times 2 times 3 all the way up to 47 times 5 factorial, which is 1 times 2 all the way up to 5. And then if we do some simplifying and canceling out common terms, 1 through 47 in the numerator cancel with 1 through 47 in the denominator. So we get 48 times 49 times 50 all the way to 52. Which is equal to this really big number. Over 5 factorial, which is 120. And if you reduce that, you get 2,598,960 possible poker hands, which is a lot, okay? And where this probability comes into play is seeing how probable it is to have a certain hand, given what you know is on the table. Okay, so if we just keep shuffling a 52 card deck and keep dealing 5 cards just one at a time, we know that no matter what, there are 2,598,960 different possible ways, things, different possible hands that we could get. Okay, now, when we are doing probability, one of the most important things that we can do is to get a sample space. And a sample space is really what we just found. It's the number of different possible outcomes that can happen. Right? So our number of different possible outcomes are 2,598,960. The most, I guess, powerful hand that you can have in poker is called the royal flush. Okay, and a royal flush is, let's see, 10, jack, queen, king, and ace, all of the same suit. Okay, so you have to be dealt a 10, a jack, a queen, a king, and an ace of either diamonds, aces, or not aces, spades, clubs, or hearts. Okay, so there are only 4 different ways that you can get a royal flush. Right, you can have a royal flush of spades, you can have a royal flush of hearts, of diamonds, or of clubs. Okay, so 4 different ways to get a royal flush. A little bit. I am kind of teaching you how to cheat. But the possible, like the probability of getting a royal flush which is where we're heading. I'm not expecting you to do this just yet. is 4, so our desired outcome, over the number of different outcomes that are possible. Which, if you plug that into a calculator, you get a really small number. Okay, which is why you never, like, if you watch professional gambling, this doesn't happen very often. And when it does, usually it doesn't matter because people are bluffing and it doesn't, like, if you have a royal flush, congratulations, but you're just out bluffing someone who's bluffing and you're probably not going to win much anyway. But that being aside, this is where we're headed. Okay, so we've done permutations, we've done counting principles, and we've done combinations, which are really just a tool of probability to see how many different possible outcomes there are. Okay. So I don't actually have any homework for you tonight because the only homework there is really just plug and chug stuff into these equations, which I don't find very interesting. So what we're going to do is we're going to hold off tonight on homework, and we'll get back at it next class when we actually dive a little bit more into probability. Okay, just keep in mind that this stuff is important to know, like permutations and knowing what they actually mean, combinations and knowing what they actually mean, and in general, just the counting principle. Those are super important when it comes to probability. Okay, so this is all I have for you. But before I actually close this and leave it open to general questions, are there questions about this example that I have up on the screen? Oh, and speaking of cheating, I do want to. I can do one more example, and then it'll be a little bit more fun with finals and stuff coming up. Say you have a test, right? And it's true and false. And you don't necessarily want to cheat, but you don't really want to study either. If there are 10 questions, what is the probability that you get all of them right? Okay, without studying, without just totally random, what's the probability of you getting them right? And the way you would do that is split this up into 10 different events. Where each question is its own event, and then multiply the total number of different outcomes or different possibilities, right? So the first question has 2 different possibilities. Second is 2, third is 2, and so on. And that would be the total number of different answer keys that you could see from different students if you had an infinite number of students, right? So if you multiply all those together, you get 2 to the 10th, which is 1024. But only one of those is right. So your probability of getting 100% is 1 divided by 1024, which again is a pretty small number. Okay, and I actually did. It was kind of a joke last year. I promised my seniors that if you could flip a coin and land on heads 10 total times in a row, I would not give a final. And it actually, the probability ends up being this because you have 1024 different possibilities, right? The same stuff applies that you see on your screen. And you'd have to get only one of those possible 10 rolls. I also did something with the grade schoolers I taught in a summer camp. the probability of the Blues winning the Stanley Cup last year, given their chances of winning every game in I think December or October and November, and the chances of that actually happening are crazy, crazy low if you just do what we just did. Okay. All right. So that is actually all I have for you. Okay. If you have general questions, I'm going to leave this open for another minute, and then I will be on Teams here in the next minute or so if you have any questions over this that is a little bit more specific. Okay. I am still thinking of how your final is going to work. I have a couple of ideas that has to do with this type stuff. I also have a final that I gave a senior that was in pre-calculus last year. Okay, so or a junior that was in pre-calculus last year. So I have that kind of in my back pocket if I run out of ideas. But it's questions like this where you have to explain kind of the reasoning behind it. Okay. So again, I'll leave this open for a minute and then I'll start a meeting on Teams. All right. It doesn't look like there are. So if you want to talk a little probability or card counting in Teams, I'll be there in the next minute.